staff, administration, and trustees, we're excited to have you here. This is a really, really cool event, and we are honored to have Z here to tell us what it was like from a first-hand perspective to be involved in a years-old overnight success that led to fusion ignition, something that a lot of people said would never happen. Now, many of you are students, and those of you who are students, if you've not yet decided on a major, or you're trying to figure out what your future career holds, take today's session as an opportunity to learn and embrace perhaps what might be your future career. If you're really excited about what you hear today, I'm excited to tell you you can get a start on that career right here at Central Carolina. In fact, one of the things you'll learn today is we have several Central Carolina alumni working in Lawrence Livermore National Labs. And our programs can help you get that started. That can be your pathway, perhaps, to being involved in the next scientific breakthrough. So one of the things I'll tell you is if you are excited about what you hear today, if it gets you energized and you want to learn more, come and talk to us here at the college and we'll help you get started on that pathway to your future. Now we're going to show you a video, and after that video, our laser and photonics lead instructor, Gary Beasley, is going to introduce our featured guests and our speaker. But for now, let's get the fun started.
Good afternoon. So it's exciting to see the people that are interested in science. I mean, you took time out of your day to come here, and I know you anticipating this. And think about you're listening to someone that was working with probably 3,500 other scientists, not all on this project, but working in various research projects at Lawrence Livermore National Labs in 1 square mile. And what they created on December 5th, 2022 can touch every life that exists now and in the future, and just make this planet a better place to live with fusion energy. So, you know, this is a historical event that you're getting to hear from somebody that's lived it for a whole bunch of years. And with that, I'd like to introduce our guest, Dr. Z. Lau and David Pope. He's going to also be in the presentation later on. So, welcome.
Thank you, Gary. Good morning, good afternoon. So thank you very much for inviting me. On behalf of Lawrence Livermore National Laboratory, I want to thank Christy and Gary and John and David for such a warm welcome. Actually, my first time in North Carolina, so I have to say, I don't know why I didn't come sooner. It's a beautiful country, but hopefully I'm going to bring some of the excitement that we have been nurturing and holding back at Lawrence Livermore National Laboratory to you all. Okay, maybe I thought it would be a good idea. I think Christy insists that I tell you a little bit about myself. So my name is Zi Lau. I am born in China. I immigrated to United States in Florida when I was 10 or 11 years old. I went to middle school and high school in Florida. So it wasn't a very good start. I have to say, my first semester in Florida, I flunked all my classes except for 2. I got a B in PE and A in math, because those 2 classes has minimum instructions. All other ones I flunked because I didn't understand English. I think the teacher actually felt bad. They changed my F to D because they felt like, wow, he didn't understand what we were saying, so how can we give him F for failure, right? So half is our fault. After that, I went to high school, and I graduated from Lake Worth High School. Then I went to University of Florida. The other thing that I kind of wanted to give you some of my personal experience is that when I was in high school, I don't know if they still take these as a military vocational tests. They basically shows you what your interests are, what your skill sets are, what your strong suits are, and then they will try and match your career for you in military. I was not interested in military, but I didn't know what I wanted to do, so I did that, and I was good in math, I was good in science, and I was definitely afraid of public speaking. So based on those 3 triangulations, my career trajectory was air traffic controller. I think that would have been okay, but I don't know. So I went to University of Rochester to study optics, and in one summer I came intern at Lawrence Livermore National Laboratory. At that point, I still don't know what I want to do, but I saw the scientists, the engineers, technicians working together on challenges that I never knew that our country was facing. And I was inspired, and after that, I decided to go back and get my PhD. And here I am. I've been working there for 25 years as a laser physicist, and last year, I became the workforce manager, and I get to go around and meet students and talk about the great science we do, and I really enjoy it. So coming back full circle, we kind of put barriers around ourselves as you know, things that you're not comfortable with. So I think it would be a good idea once in a while to push those barriers and don't let yourself or other people tell you what you can or cannot do. All right. So that's my personal story. I have about David with me a little bit. He's going to come a little bit towards the end, but David is from North Carolina, and he graduated from this program, and he's been working in National Ignition Facility with us. I think we got him as soon as he graduated so that he can't go anywhere else. He's been there for 6, 7 years, and I couldn't believe it. He's a senior laser. He didn't look that old to me, you know, because the other thing you had to know in Livermore is that our careers are people spend 20, 30, 40 years. So anything less than 10 years, they still think of you as a baby. But David's going to come up a little bit to talk about the system that he works on, and then we're going to have a Q&A section where we can talk about what it's like to work in Livermore in California and whatnot. So bear in mind with that. Okay, so you saw in the video on December 5th, 2022, we demonstrate for the very first time laser ignition. Okay, so the shot that heard around the world is N221204. That's 2022, December 04. Now, when I landed yesterday, I noticed on the license plate, North Carolina, it's the first flight, right? And I would like to think that this perhaps 20 years down the line will be generation moment that we reflect on that changes our human history. So what happened that day is that we create a plasma with a temperature of 130 million degrees by using our laser. And we produce 3.15 megajoules of fusion energy. The input is about 2 megajoules, so 150% gain. And that, by definition, exceeded the National Academy of Science definition of what fusion ignition is, okay? So this is huge, and this is what I'm going to talk about today. And decades of hard work for everybody in Livermore and all our partners in the whole fusion community, okay? So what I'm going to do is now take you back and tell you how do we get here. So first, Lawrence Livermore was established in 1952. We are about 40 minutes across the bridge from San Francisco. Our facility is called, sometimes when people call, the smartest square mile on earth. So we have a square mile space and there's about 7,000 employees. Almost half of them are PhDs, and they are pretty smart. So anyway, so we belong to Department of Energy. So we are one of the national laboratories in Department of Energy, and they are all around the country, right? So we are here. And there are national laboratories, they act like the science and technologies of the federal government, okay? So you have a laboratory that does basic science, like Lawrence Berkeley, and then national laboratories that does security labs, multi-purpose. So Lawrence Livermore is one of them, and we are one of the larger ones. Let's see. Now, so we are what we call, they're either called federally funded research and development centers or government-owned contractor operated. So unlike other parts of the federal government, we are the science and technology of the federal government. So it's a little different than other aspects of, so I think the government felt like we are more like a university, so they, a larger part of our consortium that runs Lawrence Livermore National Laboratory at University of California. So we're heavily run by University of California, but owned by the government, okay? Now, unlike your typical universities, we have a very different approach to science. And our approach that defines our heritage for Lawrence Livermore National Laboratory is team science, audacious ideas, and pursuit of extremes. So what that means is that the nation's most difficult challenges, those are the problems that we work on. We don't work on things that other people know how to solve. We only work on things that nobody else knows how to solve. So it got to be extreme challenges, and we have a big ideas to solve them. And the only way we can do it is our team science, right? So we got 7,000 to 8,000 staff, and they're world-class science, engineer, technicians. They will work together to solve the problem. Here is a picture of the founder, E.O. Lawrence from University of California, and Edward Teller. Okay, so what is the mission space for Lawrence Livermore? There are multiple mission spaces that Livermore work under, and I would like to point out a couple of them that has relevance for this talk. Is nuclear deterrence and climate and energy resiliency. So these are critical missions the government wants Livermore to participate on. And how do we solve these mission spaces, how do we support them, is through science, engineering, and computation, okay? So NIF and PS, which is the program I work under, stands for National Ignition Facility and Photon Sciences. Our mission space corresponding ensuring national security, advancing discovery science, enabling clean energy, and building future generation of scientists, which that's why I'm here, talking to you all, right? Now, you would think that that's weird, national security, discovery science, and clean energy, how do they kind of work together? Well, it turns out, this is one of my favorite slides, okay? So, this is how they work together. On the left here I think these are test sites somewhere in the deserts of Nevada. You see those big underground, those big holes. These big holes is, in the old days, we would bury devices, nuclear devices that we want to test underground. We detonate them and measure them, how big these craters are. And that tells us the success or failure of our nuclear weapons, right? And I don't know if you can see, but that's a truck there, right? So these are giant holes, football field size holes. And then a country signed a nuclear test ban treaty. We can't do these kind of tests anymore. So the way that we move forward as a country to understand our nuclear weapons stockpile is through our machine, National Munition Facility. It ensures a safe, reliable deterrence without returning to the underground nuclear test site, right? So NIF provides a laboratory setting to test the understanding of the diverse and extreme conditions of our nuclear weapons. But the science of how nuclear weapons work also is the science how stars work. So there is that cross connect, right? And if you understand the science and you can harness the energy of how science works, you can provide clean energy, right? So now you can see how emissions melt together once we understand this challenge. Okay, how do we do that? Well, we have 192 laser beams. It produces around almost 1.92 megajoules of energy. 500 terawatts of power, that's trillion watts of power. So we take all these lasers, and what we're trying to do is produce environment that's 100 million degrees temperature, 10 billion degrees pressure. That's hotter than the center of the sun, okay? So just think about a moment there. When our lasers fire, we are the hottest spot in the solar system. That includes the sun. Pretty cool, right? Pretty hot, but pretty cool. Okay. So I want to also give a shout out that this NIF laser was built, commissioned in 2009. That's a culmination of about 50 years of laser that we're trying to do this, right? So think back. Laser was demonstrated in 1960-ish, 60, ruby laser, very small in California. And around that time, scientists in Livermore lab, they are designing, building nuclear weapons. And they were thinking about ways, how do we miniaturize this nuclear weapon design so that they can do it in a laboratory setting. So when the laser was invented, somebody came up with a great idea. We can use lasers to test our nuclear weapon science. So that was a secret program, and they put their team together. In 1973, they built the first laser to do this. It was about 10 joules. They thought they could get that in 10 joules, right? Of course, you have challenges, and you overcome challenges by building bigger and more energized lasers. So they went from 10 joules to about 100 joules to kilojoule. To NOVA was 1984, was 100 kilojoules. Infrared, about 30 or 40 kilojoules, and UV. First time the frequency tripled to the UV, and that couldn't get it done. And NIF was commissioned in 2009, and we've been trying to get it done since then. So, a lot of history, a lot of failures, but for every failure, you learn, you overcome, and then you proceed, right? So that's the persistence that the National Lab has that maybe a private company could never do. Okay, so let's look at a National Munition Facility. It's huge. As a matter of fact, if I put football fields on top of the roof, you can put 3 football fields side by side. So you can have Duke, UNC, and NC State playing the football games on top of laser. Of course, I'm not going to do that, but just to tell you how big this laser is. If I take the roof off, this is what a schematic look like. Remember, 192 lasers. So you have a little control room here, and then the laser starts in this what's called MOR, master oscillating room. They start crafting the laser precisely the way the experimentals want it. And then the laser beams are propagated to these two halls, they call laser bays. So we start with very, very low energy fiber laser, nanojoules, and then we amplify 1,000,000 billion times. I just didn't make that up. Literally 1,000,000 billion times, so 10 to the 15 amplification. And then the lasers are aligned, and then they're transferred from a parallel geometry to spherical geometry where the target chamber is, right? And they align, and then they focus. The laser beams start with about a meter size, and then they're focused down to about 100 microns, right? About thinner than your hair, and then magic happens there, okay? Now, a couple of facts. Somebody say, oh, how hard is it? It's very, very hard to align this. Think about the number of laser beams and the path we took. That was one of the there were a lot of skeptics along the way. People think that this could never be done. And so laser beams, they travel about half a kilometer. And if you think about our laser beam, if you scale the size of laser beam to maybe a baseball, right? And then you multiply that factor. The alignment accuracy is, if I was here, throw a baseball to a strike zone in Atlanta. What's the stadium in Atlanta? The Brave Stadium? I have to hit the strike zone from here. That's the alignment accuracy we're looking for. But we have 192 laser beams, so I have to throw 192 laser beams, baseballs to the strike zone in Atlanta, and they'll have to hit at the same time, right? So that's amazing, but we do it routinely now, okay? The other factor that was pretty amazing is the laser takes power. So here is a capacitor bay where we take power from our power factory and we charge it. So capacitor bay is kind of like a big batteries, but our batteries are the size of your closet. We have about a couple hundred of them. So they charge the power from a power company, and they disperse the power very quickly in the fraction of a millisecond. And the enough power that we deliver to our system is about terawatt, which is it's more than the entire United States grid, right? So that's how much of the electrical energy we dump to get the laser going. So these are fun facts. Now, okay, so what the heck are we doing with this laser? What are we trying to do here, right? So the core component in all these years, what we're trying to accomplish is to achieve ignition through inertial confinement fusion, right? So those are two keywords: ignition, inertial confinement fusion. So let's kind of break it down. What is ignition? Ignition is really burning the fuel to create energy. We all have cars, so it's pretty simple. When you have your car, gasoline car, you put a fuel, gasoline, into the engine department, and the fuel gets compressed, and then you spark plug it, and that burns the fuel and creates energy that turns mechanical energy to move your car, right? That's ignition, right? But for us, our fuel is a little different, right? And instead of these pistols and spark plugs, we're using lasers. So what is that fuel that we have? And this is literally the size of the fuel. So which is also very cool. You have these 3 football field laser facility, and all the action happens in a millimeter target. Okay, so the fuel is hydrogen, which is the lightest element in the periodic table, if you look at it, and which means it has a proton in the nucleus and electron out. But there are a couple of species of hydrogen isotopes that you can have. You can have 1 neutron there, which they call deuterium. I think it's for 2. Or you have 2 neutrons called tritium, right? So if you have these 2 hydrogen isotopes and you squeeze them together, right? You need the temperature and pressure to squeeze them together, because outside of that, we know there's electrons orbiting. And electrons, they're the same charge as other electrons, so if you're trying to squeeze them, the electrons repel each other, just like a magnet, right? And in order to overcome the barrier, you need about 100 million degrees. So that's what the sun can do it, because the sun has a huge gravitational wave to do that. We don't have that gravitational wave. We use lasers to do it, right? Okay, so if you can do that, you can squeeze them together. The these two elements would fuse to the next heavy element, which is helium, right? So helium has 2 protons and 2 neutrons. And by design, you have an extra neutron. And that extra neutrons comes out with a lot of energy, right? And if you measure the energy of this isotope, the deuterium, and the mass of this particle, deuterium, and the mass of the tritium, and then you measure what's coming out of the helium and neutron, what you find was there's a little bit any mass differences. So this reaction, if you combine the mass, is less than the starting point. Okay? We all know Einstein had this equation, E equals mc squared. So energy and mass are interchangeable by this constant, c, which is speed of light, 3 times 10 to the 8 meters per second squared. So if you square that, is 1 times 10 to the 17. That's a large number. So that means the small mass differences convert into huge energy. And this is essentially what's going on, right? So this reaction produces helium and neutron and a lot of energy that carry out by this neutron. How large? So if you want to think about energy density, so that means amount of energy per unit weight, right? If you think about burning coal, you can burn, you can get 24 megajoules of energy per kilogram, right? That's a chemical reaction. So our DT, which is the deuterium-tritium reaction, can get 3.4 times 10 to the 8 megajoules per kilogram. So that's 10 million times more energy output, right? That's the difference between chemical reaction and nuclear reaction, right? So with very little fuel, you can get a lot of energy out because you're accessing this nuclear regime. Okay, so the other part I promised to tell you about is inertial confinement fusion, ICF, right? So this is how this whole fusion process works. So in the field here is your DT, hydrogen isotopes, tritium, deuterium. And then what you do is you put a layer of hardened material around it, okay? And then you put your energy on this shell. And the shell would get burned. And what happened is that if there's enough energy deposited in the shell, it basically would explode, right? And then you would generate a rocket effect. So when they explode, the shell explodes this way, but there is an opposite force driven inward. They call it the rocket effect. If you imagine when rocket goes up, it goes this way, but the fume is going that way, right? So the energy is pushing down, so the rocket goes out. This is the same thing. So the shell explodes, but there's an equal opposite driven, okay? And so what happened is like now your fuel starts to compress. They implode, right? As you compress, the same amount of fuel is getting smaller and smaller area. That means temperature in that fuel gets hotter and hotter. And if you can press that, implode that, and it will get so hot, if you get 100 million degrees, then you can start getting this fusion event happening, okay? Okay, now, here's the key. You want to keep that fusion event confined enough so that it will burn out the rest of the way. So remember that neutron comes out with a lot of energy. So if the thing is compressing and then the neutrons releasing from the middle, it will radiate and deposit energy to surrounding parts of it and get the other part burning. And if you do that correctly, that the whole thing would burn, right? So that's the key. I think these two were pretty easy, but keeping this compression, the inertial confinement part, that was a hard part that keeping us working for many, many years. Okay, so boom, you burn the fuel and you get the energy out. So that's, in principle, how is it done. In National Ignition Facility, this is how we do it, right? Because that's just schematic. You have to actually put it into work. So here is our fuel. And the outer layer we play with different materials. And right now we use high density carbon. So basically make diamond shells and all that. How you like that, have your engagement ring, right? Okay, so it's a millimeter there. And then they are placed in a tin, and we put it in a canister. Okay. Why did we do that, right? Imagine, because in my previous view graph, I said the energy have deposited into the shell so that it basically blow off and create that implosion process. Think about how hard it is. Laser beams are pinpoint sources, right? So think about, imagine my field millimeter is the size of basketball. I have to implode that, compress that to the size of P. So if you have laser beams hitting that, whatever spot that you don't hit, or you don't hit it uniformly, you're going to start squishing, right? And that reduces your ability to compress. So that was a very hard, challenging problem. So at National Ignition Facility, our approach is basically solving the problem by putting the laser beam not directly on the target, which what we call direct drive. We say, well, we're going to basically put the target inside a canister, and we call Hohlraum, which is German word for just a can. A canister, then we use laser to heat the canister, and it creates X-rays. And X-ray is the thing that does implosion, right? So it sounds complicated, but it's not. This is how your oven works, right? If I give you a laser beam, I give you frozen chicken to cook, you can use laser to cook the chicken, but only the part that laser seating it is going to cook. But if you think about it, if you take a metal box, you take the laser, you heat the box, and you put a chicken in the middle, and it will cook evenly, right? So this is the same concept, but it's not as efficient. So laser beams hits this canister, and it creates X-ray, and X-ray is the thing that drive that implosion process. And basically, a millimeter targets get to about 100 microns, 200 microns, and the center, the 10, 50 microns in the middle, get hot enough, 100 million degrees, 10 billion pressure, and then fusion begin. And if you can hold that implosion process long enough for it to burn out, then you get the gain. If you don't hold it long enough, the whole thing's over before you can propagate the gain, right? So that's the trick here. Okay, I'm going to walk through an animation on how a laser works. Okay, so it starts out, it's 24 hours facility, and I think one of the graduates actually, it's not in this video, but he operates the laser. So we have a 24 hours facility, people operating laser, and so we have an operation room. And if you look at it, you start by charging the capacitors, right? Getting electrical power into those capacitors. And in our MOR room, where we sculpt the laser pulses precisely shaped the way we want it, right? And then we replicate that 48 times. And those lasers are going through either side of the laser bay for amplification, right? And then we amplify the heck of it, right? A million billion times. Every time you go through the amplifiers, the energy gets more and more. And here, it's 8 of the beam lines, right? So you can notice that it's a pulse, which is, as it goes through our amplification system, gets amplified. And in between, we also do spatial filtering, which cleans the laser beam so the quality of the beam is maintained, so we can focus them as tight as we want it. And then what you see is the beams are starting to go in from parallel geometry to spherical geometry through the switch yard. And just before it hit the target chamber, we change the light of the laser, which is by magic. Literally, and then we focus all the laser beams to the canister, right? The Hohlraum we're talking about. So you notice we don't hit the target directly, we hit the canister, and it heats up and creates X-rays, which squeezes the fuel. Come on, fuel, let's go. And create fusion. Here we go. So, sounds simple, right? What? You had it since 2009. What took you so long, Z? Well, it turns out it's really not that simple. So what here I have a graph here is moving, so I'm going to have to catch up. It's year 2009, 2010, and then on the vertical axis is target gain. That's if the energy out versus energy in, right? So you can see we start with 0.0001. That means our gain is less than 0.01%. And over the years, different color showing different technologies, different ideas we're trying to overcome the challenges we have. So So we have a lot of failures, but we learn, we figure out different ways, and then all of a sudden, this is actually what most people thought. This is actually 2 years ago when we did this one, and we thought that this kind of gave us scientific proof that, because the previous lasers, what happened is that they get to a regime where they discover new science, right? This is what happens when you push the boundary. You've literally discovered new science you've never seen before. You're like, uh-oh, we've never seen this before. To scientists, that's really good, but politicians, they don't like it. You know, like, what do you know? Well, we don't know, right? And it's like, we never saw this before, and then you study, and it's like, okay, plan B, you build a bigger laser, right? So that's what happened. That's what happened the last 4 or 5, and I would say up to this point, we were like, okay, are we going to hit that barrier where we said, this is a new thing that we discover and we can't overcome it. We know we can't overcome it. And when that shot hit, and we thought, okay, this is pretty much, we're there. We just have to optimize it. We just need to find the sweet spot. And sure enough, we did it, right? So, okay. That's it. So 2.05 megajoules of laser delivered to the target. We got 3.15 megajoules fusion now. Okay. Okay, so what does it mean? Well, and I told you about energy density, right? How this is really, nuclear energy provides such a potential important for energy, clean energy. Well, because what do you say, well, where does DT come from? Well, DT is hydrogen, and you know, hydrogen, you can get hydrogen from water, and there's water everywhere, right? So every gallon of seawater contains fusion energy equivalent to burning 300 gallons of gasoline. And last time I looked, we have oceans of seawater. So that means potentially unlimited source of fuel. All you have to do is scoop some water out, and we find it, and you can burn it, right? So that's really, really important. Now, this is where it comes to you. The science, this is a great quote. The science of today is the technology of tomorrow, which coined by Edward Teller, one of the founders of the lab. So what we just did is demonstrate the science of it. The next part is developing technologies to make it a power plant, right? So we have established the scientific foundation. We have demonstrated in a laboratory setting how that it is possible to do this, okay? But to turn this to energy, there's going to be a next challenge, right? And some people think just the challenge that we did to get to this far, the challenge is just as hard to go forward, right? Which is scary. I mean, but it should be exciting for you because that's not going to be my task, I don't think. But so we have been traveling the country, but it's so, I think the challenge is monumental, but the benefit is just as big. And what we're trying to do is build a consortium, a partnership with government, private industry, charitable industry, academic institutions to build the foundations to tackle this challenge, right? So we will need a lot of people working on this, and hopefully will be few of you, all right? Or many of you. Okay, now I'm going to pivot a little bit. For you not to think that's the only laser we have. You know, some people say Lawrence Livermore National Laboratory stands for lasers, nothing but lasers. That's what I say, because I'm from the laser program. So I'm going to give a few minutes about other lasers that's just as exciting and maybe not as challenging, but it's pretty challenging. So our core capability, the reason why we could do this, and our experience of building this NIF laser has established we are like top laser science engineering. We understand how laser matter interact, right? Because we have to do that. And the optics that we make are just first class. These are meter-sized gratings for compressing short pulses. We also know how to design and build and operate very complex systems, so you have to do that. And then high energy density physics, right? How to make targets to interact with that. So those are our core capabilities that allow us to have these technologies that one of a kind. We have some of the best, highest, brightest laser diodes. We have pump lasers that nobody else have. We also have a fiber drawing tower that we can make custom fibers for our purpose and for the nation's purpose. Highest average power grading. I talked to you a little bit about that. We have a gas-cooled short pulse amplifier as well. So all of them are world class. And so we have customers that comes to us, government facilities, other governments, for example, other countries, they want state-of-the-art laser system. They come to us to build it for them, right? I'm just going to point out a couple of them, like NIF, we talk about that, the world's most energetic laser. And guess what we did? We also turned 4 of the beam of NIF into a short pulse. So that becomes the world's highest petawatt system, right? And let's see, we also had the world's highest average power tunable laser. Atlas, which I worked on that when I was a student, is to enrich uranium. So everything here is the world's brightest, the world's highest average power, et cetera, et cetera. Here, I also want to point out, specifically DPAL, high average power diode pump alkali laser. This is the system that David worked on. David, you want to come tell you about your system? No one steal his thunder.
Appreciate that. Thank you, Z. I'll try to follow that with a little information about myself. So the diode pumped alkali laser is where NIF's mission is to create fusion. Our mission is called a directed energy system. So we're basically trying to create a laser that can output a lot of energy and put that onto a target, wherever that may be. So this was the first project that I worked on when I started, and I've been working there since 2016, so it's 7 years. And I just moved on to another project. So I put pretty much my whole career at the lab into this, and it's been super successful. The performance actually reached a level where it's gone classified, so it's doing great, trust me. So just a quick explanation of how it works. We take the advantages of solid-state lasers, which have very high efficiency, so energy in versus energy out. They're also very simple geometry to set up those systems. And gas lasers, which you can have very high output power and good beam quality. And so basically what you do is you vaporize an alkali metal, hence the name, and mix that with a stream of gas, and that is your amplifier. Where NIF uses big, glass optics, we use a vaporized metal and gas. And what that does is allow you to combine these two advantages into a very powerful and efficient system that is highly scalable. And what that means is we can make it bigger and better by just putting in more light. So just make more diodes to pump the system, you get more output. So that's the big advantage of DPAL. A little more about my experience is I graduated from the Laser and Photonics Technology here in 2016. And right after graduation, I packed up the Toyota Camry and drove out to Livermore to start working at the lab. The reason I say this is it's so exciting to see all the students' faces in here that are interested in this. And I just want you to know, if this is what you want to do, this can be you, if you want. Don't be afraid to fail, just be afraid not to try. So when I first started, what I did was what's called production diode characterization. The DPAL system is pumped by semiconductor laser diode arrays, which are basically grids of miniature lasers that are mounted onto a little metal structure. And we use many of those mounted onto a larger structure that we call a backplane to pump the vaporized rubidium. My job was to test the diodes. So every diode we got in, I would run it through this proceduralized group of tests and see, does this performance, are these the specifications we agreed on with the vendor? So I did that for roughly 2 years. Once I got comfortable with that, we started doing a lot more experiments. Investigating specific things and curiosity as to how the diode arrays behave. And that was really cool because now I get to start actually setting things up and having a little more control of the decision making there. So it wasn't, going off a procedure. I was actually being asked, what do you think? How do you think we could do this? And this is, PhDs like Z and world-class engineers in the room, and they're asking me what I think. So that was a really cool experience. So I did a lot of experiments. We've learned a lot about the diode behavior. We were able to improve the system many times over. Following that, at this point, we were at the third version of DPAL since I had started. So we had been successful, made it bigger, been successful, made it even bigger. So at this point, the backplanes, the structure that we mount all the pump diodes on, they needed someone to build that. And it was kind of like an empty room, and I was the one guy that walked in. And they said, why don't you try it? And so the current iteration of the DPAL system, I actually hand-built every backplane in that system. So that's something, you can be a student here, go to the lab, and directly build something that's actually in one of these projects. So that was extremely rewarding and really cool to do. And my most recent assignment has been to, I've moved on to a new project, and I'm actually building the amplifier slabs, which are big pieces of doped laser glass that amplify the light. And so I'm assembling these slabs in a mosaic of different glass, and then filling the gaps with epoxy and mounting all that in metal bezels to put into this new laser system. So that's my current assignment, and it's been a blast. So the reason I came here with Z was to help, sort of show the connection between CCCC and Lawrence Livermore, to just be, if you're interested in this, we would love to have you. So I'm going to throw it back to Z, and then we'll open up for questions at the end.
Oh, well, he was being humble because I'm sure that backplane wasn't there like no other one like it.
Oh, it was actually it was 3D printed, so it's completely unique.
Yep.
Nothing else like it.
Yeah, that's the thing is like we don't do things, we don't copy other people, then people copy us. So, but that's fine, right? All right. So. I think I have a couple of slides, but I think this is important. So, I think earlier in my slide, I say, one of the things that distinguish how we approach these difficult, challenging projects is not just throw people at it, but throw people of different diverse background, diverse discipline. So if you look at our S&T, science, technology, engineering workforce, we get basically all levels of discipline covered, right? Not only that, I think we say it, but it's like if you have a question about a subject, there's an expert somewhere in that square mile. You just need to find it. Usually that's the hardest thing, to find that person. But once you find that person, they would tell you everything you wanted to know. So that's it is. But if you look at this other chart here, you talk about all different disciplines that we have. There is PSTS, I know that because now I'm a workforce manager, so I have to know all these acronyms. It's professional science technology, right? These technicians. So we work very, very closely, right? Like David said. The reason why they ask people like him is like there are people like me with PhDs. I'm not good at my hands. If I was going to build things, it's going to fall apart within 5 minutes, right? So that's why we ask him, because even though we have some ideas, to take that concept in our head and actually make it work, we need people like him who has the gift to be able to build things with accuracy, with consistency, right? So we work very, very closely to be able to translate ideas, however vague, and put it into real production, right? Real devices. That's the really exciting thing about Lawrence Livermore National Lab is the applied science, right? We take cutting-edge science, fundamental science, and we basically make it real, right? And that's kind of the thing that I think makes our work worthwhile, because when I go to work every day, I don't know what I'm working on, but I know the things I'm working on, no one has worked on before, and that's exciting. Okay, final slide. We are very we have a lot of dedication into outreach and education. So we go to elementary schools, we go to middle schools and high school, and trying to outreach and get people excited about science. We also invest heavily into our staff. We put millions of dollars into our educational fund, so when the staff come to Livermore, they can get higher degrees, and we'll pay for it, right? So if your associate degree, you can get your bachelor's, you can get your master's, you can get your PhD, and we'll pay for you while you're working in Livermore to get your education up and going. Because the biggest thing we have going for us is our people, and so by educating them, we're really investing into ourselves. Okay, let's get ignition. So who's up for that? That's it. Thank you very much. Wait, you want to just... Okay, we'll want to stand behind the screen so that you don't...
So we have a few minutes
There you
left
go.
for some question and answer from the audience. If you have a question for either David or Z, I'll come around with the mic, and they'll be happy to take your questions.
So, looking at this, I see like large quantities of numbers and small quantities even, and then I'm wondering how did you guys deal with the numerics part of this whole engineering aspect? Like, was there ever a time when you had a problem that maybe the stability or conditioning was not viable to work with, and you had to tackle it a different way or anything? Was that ever an issue or anything like that?
Actually, I missed the first part. Could you repeat that? I was distracted by the scrolling screen.
So I'm wondering about the numerics part, when you translated the mathematics into the computer science or coding in particular, right?
Yeah.
How did you really deal with problems that might have been had a lot of instability or anything like that, like the conditioning and whatnot? So let's say you had a problem that maybe with this precision, it was not feasible to work in this method. So I guess, how did you handle that? How did the engineers really deal with that?
That's a tough question.
Yeah, that's
Can we warm up to easier question? Let me think about that. That's a really tough question.
favorite color maybe.
You were asking right over there, but I mean, so engineering, applied science, and theoretical science, they have to work together, right? And there's a lot of interactions where people have these great ideas in theory, and then we're going to have to find data or design experiments to validate that. And once we understand that, then we can try and transfer that into an actual technology platform, right? So I think what you're asking is that, how does that process work? That process works very organically, sometimes very linearly, sometimes it's not. I think learning, problem solving, there's no right way and wrong way of doing it, but you need the skill set, you need some experiences, and then the thing that I think helps me a lot is a lot of problems, I go around and I talk to people, and then idea will come because people have different perspectives, and sometimes those are the most informal way of solving problems. So, okay.
That's why the math is teamed up with computer science in that chart.
Yes, you're right. Okay, that. Well, it's, for example, nuclear weapons stockpile stewardship, that's our program. That's the critical mission. So our mission, basically, I think I've been told that every year the laboratory have to sign a letter saying our nuclear stockpile is working. Well, how do you know it's working without detonating them, right? The way that we have designed with this program is we're going to do computation, the heck of it, right? So that's where I have supercomputers. Livermore usually have the top 5 supercomputers in the world, and they're cranking out. They put the physics of nuclear weapons into the code, and they run the code, say, well, it's going to work or not, right? To test the stability of that. But as you know, garbage in, garbage out, right? So what are the input parameters? The input parameters would be the weapons design, the materials, not materials brand new, material that's sitting in the ground in different conditions, humidity and temperature for 20, 30, 40 years. So how do you know that material, how it's going to react when you detonate it 100 million degrees, for example? You don't. How do you do that? The NIP provide the data to go into computer programs to simulate that. So that's how all that plays together. Thank you. Excellent question. Thank you.
Hey, bro, what's up? So you said you got like all this energy, right?
Yeah.
So like, how do you store it?
Yeah. Because that's going to be your problem when you come.
Oh, really?
So
Okay.
science, I do the science and you do technology. No, so this is this demonstration, right? So we just demonstrate that it works. We measure the neutron yield, and we know that we've gotten the more energy out than in, right? So our facility does not have the design. It's not designed to capture energy. This only designed to test and measure, right? So if you have a power plant, what you would do is you would have a thermal blanket around the target chamber, right? So when the neutrons comes out, instead of just going through air and let it cool, it would capture that and convert that energy from the neutrons, deposit and heat up some kind of thermal blanket, and then you can boil water and make electricity. It's our 21st century is always work on boiling water and making electricity, yeah.
So earlier you said the chamber can reach 120 million degrees. How would you go about cooling that in NIF, as well as the surrounding lasers? Since that would be known to heat it up.
Right. That's why the fuel is only this big. The chamber is 10 meters across. So basically, it happens very quickly, and the design of the chamber is basically to cool that process, right? So we don't have to cool it because it detonates, and then the energy disperses in that 10 meters and is contained in that target chamber. The chamber is, what is like aluminum plate that's like 10 centimeters plus another 300 centimeters of concrete, right, to contain that, right? So if you want to create energy, you don't want to cool it, you want to capture that energy. And the lasers are way out there. So if we're in a target chamber, the lasers are probably in the parking lot, right? So it's not going to get back to the laser. Okay. Yeah.
Sir, good afternoon. Nuclear energy was touted as a clean fuel. Does this have any waste?
Right. So as you know, the nuclear energy we talk about these days are fission reactions, uranium, plutonium, that basically decay and chain reaction, right? So what happens when you do that, the end product is these radioactive fuel rods that you don't know what to do with. You have to bury in the mountains. So here we have hydrogen isotopes, right? And you burn them, that's it. So the only things that you have to worry about is that the chamber will become radioactive over time. So then you have to deal with that. But then you don't have radioactive fuel rods that you have to manage, right? And they're not dangerous. You have to bury in the ground, why not? So great question, thank you.
So whenever you were showing kind of the chart of all the energy released, what was responsible for like how massive the differences were in energy released? Was it just changing a bunch of parameters, or is there a bit of kind of, or is it not always consistent how much is released?
Oh yeah, so in the chart you see there was a lot of graphs. So I think we thought, so the Laser Commission 2009, and we thought by 2012 we would get it. So we thought just crank the laser up, and then we're done. And what happened was like crank up, we get more and more, and then it kind of plateau. And then we're like, oh, what the, So we look back there and figured out what the problem is. So a lot of times is that when you look at, it's never linear. So when you look back, you can think, oh, there might be these 5 problems. You don't know how to solve them. You don't know which one is more sensitive. So what you do is you basically maybe tackle each of them, a combination of 2 at a time. And you do it subscales and figure out how stable is it, how easy to overcome. So a lot of this up and down is maybe trial and error, looking at different technologies and test it out whether certain parameters is harder to do than others, right? I mean, it's very complicated because the laser has about 20,000 control points. Right? We have to write an entire computer program to operate the laser. So I would say, in the beginning, when things didn't go well, it's like we have no reproducibility. Every shot seems almost different, right? So you don't know the spaces, parameter space, you don't know the sensitivities. You can't even say there's 2 shots if they don't get the results. Are they different because the laser, or different because of mechanics, right? So I think it took a lot of time to build the data and look at different parameter spaces to understand what was the critical parameters, right?
Hi, thank you so much for coming to Central Carolina Community College. I just was wondering, so I know it took decades to achieve this goal, and I know there's not really an estimated time frame that you probably have, but do you happen to happen to just guesstimate a time frame on which we could use that energy and turn it into, like, when a power plant would be available for government public use, to where we can actually start using that energy?
Okay, so the question is, how long will we get clean energy?
Yes. Sorry.
If you saw the news interview, what was the year? 5, 10, 20, 30? It depends how much money you give us, pretty much. I mean, at the end of the day, it's a unique technology, right? We already know what the technology is, right? I'll just kind of give you, we need to switch, we have flash lamp right now. Flash lamp is extremely inefficient, like 0.1% efficiency, right? So if you go diodes, what efficiency do you think you get?
We saw in depower like 50,
right.
55%.
So if we go diodes, you can get much higher efficiencies. That means, you know, the target gain doesn't have to be so high in order to make it back. So that's one. The other thing is that we shoot our laser maybe once a day, twice a day, because we're doing experiments. You want a power plant, you have to shoot this about 10 times a second. Okay? That's going to be a challenge, right? But we know the technology, we understand technology, but basically being able to invest in technology and make the technology economical to when you build a power plant, it's economical. That's kind of like what you want. And that's why we are going around looking at private industries, looking at government agencies, looking at academians, to have people, all hands on deck, to think about solutions. If each one of us can solve some of these technical problems, and as a whole, we can probably get there much faster, right? But at the end of the day, somebody's going to have to get the money to get things rolling, right? So thank you.
Hi, thank you for the amazing talk. I love the X-ray and chicken example. So my question is very similar. So I know you mentioned that your input power is about 2 megajoules.
Yeah.
I'm wondering, like, what's the overall input power of like charging your capacitors and lasers, and the overall system efficiency?
Yeah, that's really bad. Right. That's why it's in science, right? So I think we'll probably put like 400 megajoules electrical power into it, and that turned into 4 megajoules of infrared light. Then we have to frequency convert that into UV. That throws out 30 or 40%. And then we have to focus that down to the whole realm, convert the laser to X-ray. So all those losses combine together, right? But like I said before, we understand that. And those are not the only way. Like this laser, the architect is come from the 1960s, 70s, the flash lamp. That's the 80s technology, maybe 70s technology, I don't know. But we already know the new technology, right? David's working on it, right? So all the diodes that we're working on, that is going to be the future. That would be one way to basically cut down the efficiency tremendously, right? So I think the challenge is there, but I don't think it's insurmountable, right? I think we just need to work on it.
Thank you.
Thank you.
Okay. Hey, thanks for the talk. My question is if there is a theoretical way or any ideas to lower the amount of energy needed to achieve ignition in the first place, and then like ideas for sustaining it for longer than just like, I guess a second ago you mentioned like firing the laser multiple times over and over again. But is there like a continuous way or a non-pulsed way? I'm going to have to go back and talk to the physicists. But there are a couple ways people have played around with the idea, right? Remember, ours is indirect drive, so we have to put extra energy because we are not hitting the target directly. You have to hit the can. So in a way, we're throwing away this conversion process from laser to X-ray. So if you hit it directly, that would mean you need less, but you need better control. So as a matter of fact, there is a laser lab in Rochester called LLE, Laser Engineering. So there's a smaller scale, and they do their experiments on direct drive, right? So that's one way that you can lower the energy input to the system. And there was another idea that I know about 10 years ago, it was pretty cool. and which is what they call, I forgot what's it called, but the idea would be to kind of more like if you think about the engine analogies, using the long pulse, which what NIF is, about nanoseconds, to compress it, and then, but you don't use all of it. You don't need all of it to compress and then to ignite. You compress the field with long pulse, and just when it's compressed, you shoot it with a short pulse, very short pulse, to spark plug it, right? So that was another idea I think Japan kind of pioneered. Maybe that would be one way. But the exciting thing is like, once we demonstrate this part, now you know it works, then these other ideas we can go back and revisit, and that might be a much easier way than trying to, do all three at the same time. You don't know how to overcome it, right? Yeah.
Hi. So you mentioned that you guys are using all this energy to power the capacitors for the lasers, and it's coming from a different source, I'm imagining. How are you guys mitigating that in relation to like the power demands and needs of like the local and neighboring like counties or cities and whatnot? And how's the public response to that as far as support in the experiments?
Yeah, so even though we draw a lot of electrical power, we have a dedicated line, and I think it's only like take a couple minutes to charge. So it's not a huge drain in the local power infrastructure, right? So we only shoot that a couple times a day. So I think those are very quickly. It was surprising to me how little we use the power plant resources, right? So yeah, so it truly is not that bad.
I have a question for Dr. Xi. So has your role in the lab changed over time? Because I know you've been there since 2001.
Yes.
Has your position been the same throughout that whole length of time?
Yeah. So this is the interesting thing about the lab is you can go, when you start it, you can be a researcher or you can be in management. And you don't have to move up to management to advance your career. So I've been in the lab for 25 years, and I was a laser researcher for that time. And I, just like David, about 4 or 5 years when the project ends or when I get bored, I move to a different project. So I work on that chart. I work on maybe 4 or 5 different projects. And my responsibility got a little bit more, but my role was still the same, right? Until this past year when I took a management role because of the challenges of workforce. So you can have that and have other people who can, change the position very rapidly. David, do you feel like people kind of stay the same, or there's a lot up and down?
I think that there's certainly opportunity to change up what you're doing if you want to. So for me, I get bored kind of fast. So I'm like, all right, I got this down. I want to go do this. I want to go. If you're more comfortable just being really good at the thing that you do, there's absolutely a place for you to do that. No one is going to force you to do something you don't want to do. And there's always a position that, hey, we need someone to be the guy that's really, really, really good at this and knows every in and out. So either one, it's whatever you choose.
Right. So the analogies, there are some people who go there and then they dig a hole, meaning that they were interested in one topic and they just dive into it and they know more than anybody. That's why we have all these world experts. They dig a lot of holes where they are the expert, they know more than anybody else. So those local experts, they don't work on one project, they're kind of consultants, right? People have a problem and they're like, oh, you know what, let's get that person involved about this particular challenges. So they would get asked about it. Or you can have people who move around, who has a broad skill set and they can't stand still. So they find challenges. And so their skill sets would be movable, but they don't dig the hole like some of these experts would be, right? So that's great because it depends on your personality. Some people like that stability. They like something very, very, very passionate and they just want to sit on that subject and be the best. You can do that. Or you can move around and work on different things. And there's a lot of projects. I mean, how many lasers do we have?
I don't know. Hundreds.
Exactly. I don't know either. Yeah.
Hello. Thank both of you for coming out here. I just had a really quick question. So what attributes would you say someone would need to be successful at either NIF or any other laser laboratories at Lawrence Livermore?
I'll let you take that one.
Sure. I'll just go with what worked for me. Number one, just not being afraid to put yourself out there and try new things, because the thing that's 100% going to happen is you're going to fail at something. And having the ability to bounce back from that and learn from that every time it happens is absolutely essential, because we fail all the time. And that's what's brought us to the success, that the reason Z is here is built on hundreds and hundreds of failures.
Good failures.
Good failures.
Carefully designed failures.
Learning opportunities.
Yeah.
So that's one. Obviously, organization helps. Responsibility helps, but just being willing to learn, being willing to put yourself in a situation where maybe you're not 100% an expert on what's going on, and being willing to put yourself out there and say, I don't understand this. Because when you're at the lab, the cool thing is you're in the room with people that know everything there is to know about this, and they cannot wait to get to the nearest whiteboard so they can tell you about it for way longer than you wanted them to. So
PhDs, they do that.
Yeah. So I mean, just don't be afraid to put yourself out there. Don't be afraid to try new things. If that's something that you think is good for you, you'll absolutely do well there.
I think the number one is willing to learn, because what I tell people is that what you learn in the classroom, when you come to the lab, that's not what we do. I mean, we don't do exactly that, because what we do is not in the textbooks a lot of times, is these knowledges that pass down from generation to generations, scientists to scientists, technicians, right? Because we do things that nobody else do. So these things are not in the textbook, because no one had done it before, right? How will you write something like that? So your ability to learn, willing to learn and be curious about it is number one, because if you're not going to learn, taking you what you have coming in, that's not going to be enough, because the idea is that we want you to be curious, you have some foundation that we can build on, and we're going to teach you. I think that's the other thing, is that we expect, it's our responsibility to get up to speed and endow with you the knowledge that we have accumulated, right? Because some of that is classified. By nature, we don't publish it, right? So.
Yeah, I can personally offer my experience is that, I graduated and I thought I was like this smart laser expert. And
you are.
I'm getting there. And I show up and they start going through, okay, this is the experiment we want to do, and we're going to install this optic in this wave plate, and I think I made like a Homer Simpson sound, like, dole, what? And so it's going to be all new stuff, and the good news is it's all really cool and really interesting, and it's totally unique.
I mean, I felt like that the first 7 years when I would have my PhD, same thing too, right? So, yeah.
We got 2 more questions.
Okay.
One right here and one across the room.
All right.
Thank y'all for coming, first of all. As a former laser photonics student to the current ones, myself and the guys that are here with me, what are some things that you can give us advice on as far as what Central Carolina did for you as far as getting the job that you have through Mr. Beasley and the program, and what you did as a student to do better or to be a better student beyond what you already knew in your personal experiences?
Well, for me, it kind of turned my life around. I have a 4-year liberal arts degree, and I graduated and I discovered maybe this isn't for me. So I wanted a career change, and I kind of didn't know what to do. And my whole family is actually from Dunn, just over the hill. So unbeknownst to me, Gary was actually a family friend. So my grandfather introduced me to him, and then they took me through the laser program, and I was like, I had no idea something like this was hiding out here. So for me, it completely changed my life. In the second year of the program, we had Rob Campbell, our laser systems engineering superintendent. He is now anyway. He came out with another lab employee, and they sort of did a recruitment thing. And I talked to them and said I was interested, and went through the interview process, and that was that. And that at the end of the year, I was out working there, and
I'm not planning to leave anytime soon, and I'm loving it. So as far as what you can do, take your assignments seriously. Don't just try to get through the coursework and figure it out later. Try to learn the concepts and put effort into it and try hard, because the one thing that keeps coming back over and over and over are the basics and the fundamentals. If you learn those, you're going to be just fine. But if you don't put the effort in, it's going to be really hard.
So the question I had was, when you find new technology, there's always something that comes out of it. You always find more technology out of it. Flying brought us to space. The nuclear bomb brought us nuclear power. Are there any technologies you think may expand from fusion?
Oh, yeah, one came to my mind.
You can't even count them, probably, right?
Yeah. Well, when I moved into my office one year, I saw a little board from previous occupant, and it was looks like a flying saucer. And the idea is, we're in a space age, we can go to the moon. We can't go any further than that, especially with people, because when we go, the fuel, the rocket fuel, the solid fuel, they're so heavy, right? Most of the energy is basically carrying the fuel, which you burn out, right? So remember that energy density, 10 million times? If you want to go other parts of the solar system besides the moon, you need to carry enough fuel to power yourself. And if you have a fuel source, a technology that's 10 million times lighter, that's a way that you can go to different planets. So you imagine having a laser NIF and a flying saucer, a spaceship, and then you fire a pellet behind you, you zip the laser, creates a fusion reaction, give you your impulse, and then you can go to Mars, maybe. I don't know, but how's that? That's one idea.
Another sort of just kind of an addendum to that question, not specifically fusion, but you saw in Z's presentation, he had all the systems that came before, right? Each one bigger than the last. All those, different versions of those systems, every time there's something we learn and there's a process developed or there's infrastructure that's built into the lab, and we use that over time for future successes. So, the successes of new things that we try can actually be a curve rather than a straight line, because we're continuously developing on these past technologies. So there's always something new and unexpected out there with what we've learned so far.
Wonderful. Thank you guys so much. Thank you for being here with us.
Thank you.
As you might imagine, am I on? As you might imagine, a big part of our mission here at Central Carolina Community College is learning and access to learning. And so the purpose of learning, or one of the purposes of learning, is growth. And so, Dr. Lau and Mr. Pope, we so appreciate you bringing your experiences, your learning here to us at the college today, so we can grow and learn with you. Faculty, students, staff, community partners, friends, thank you for sharing with us today. We are so excited to get these two out here from California, and so thank you for making this a successful event today. And we have just a small gift for you guys as a token of appreciation. So thanks, everyone.
Thank you.